In this video, I'm going to talk about hydronic controlling systems, but specifically I'm going to be talking about relays. Now, relays in hydronics and relays in any other application is still basically the same principle. So the relay is an electrical device consisting of a coil and a set of contacts. The coil and contacts are isolated. That means protected from each other. There's no electrical connection between the coil and the contacts. It's designed to be used where one circuit must control another circuit. A coil is a spool of wire that's wrapped around an iron core. When the wire is energized, electricity is applied to it. There's a magnetic field generated. This field pulls in an armature that closes or opens a set of contacts. When a relay is shown in a schematic, it is always shown in the de-energized or normally mode. Every coil in a relay has a voltage rating. This rating is the voltage that you may apply to the coil. The ratings are normally 24, 120, 208, or 230 volts. But you may not apply 120 volts to a 24 volt coil, and you cannot use a 24 volt supply on a 120 volt coil. The coil voltage is extremely important. Do not use any other coil for the specific voltage you want. The coil rating is normally stamped on the side of the relay or printed on a sticker. The coil is a load in a schematic circuit. It uses power to do something. A coil can be checked with an ohm meter. An OL reading indicates that the coil is open. A 0 reading indicates that it's a shorted coil. There should be some number reading other than OL or 0. Relay contacts are the switching device of the relay. When contacts are drawn in a schematic, they're treated as open or closed switch, and they're drawn in their normally open or closed position. Normal refers to the position of the switch while de-energized. Relay contacts come in two positions, normally open or normally closed. Relay contacts that are attached to the armature that is moved by the magnetic force of the coil. Relay contacts have metal points that come in contact with each other. These points complete the circuit. Normally open contacts are the equivalent of an open switch. When the relay coil is de-energized, the contact is an open switch in the circuit. When the relay coil is energized, they close, just like turning on a light switch. When the coil is de-energized, they open again. A normally closed contact is a closed switch when the coil is de-energized. When the coil is energized, the switch opens and stops the current from reaching the load. When the coil is de-energized, the contacts close again. The contacts are rated with the number of amps they can control. Contacts are also rated with the type of load they can control. This would either be inductive, like a motor, or resistive, like a heater. With inductive load, the amperage spikes when it's starting. With resistive loads, the amperage remains fairly constant. Make sure the contact ratings exceed the maximum amperage that the load is rated for. If you don't do that, the relay will eventually fail. So let's talk about the sequence of operation in a Mars brand relay. And there's different brands, but this is the same. This principle works across all brands. When the relay is de-energized, there's no power across the coil. The contacts between points 1 and 3 are normally open. The contacts between points 1 and 2 are normally closed. The relay coil is energized with 24 volts. This closes the contact between 1 and 3 and opens the contact between 1 and 2. So this is the schematic symbols we're dealing with. We have a relay coil, we have a normally open contact, and we have a normally closed contact. These are symbols you really need to know. So let's look at example 1 here. Okay. So when we look at example 1, we see we have a normally open contact to the top light bulb and a normally closed contact to the bottom light bulb. Switch 1 is open, which means the coil is de-energized, not getting any power. So in switch 1, C1 is not energized. Normally open contact, C1 is open and the first load is not energized. The normally closed contact is closed and the second load is energized. So again, we have a path for current to go through this load, but we don't have a path for current to go through the first load. And we don't have a path of current to go through that relay coil. So in this example, we've now closed the switch. We've energized the coil of C1, which has opened the normally closed. In other words, it reverses position and closed the normally open. So the top bulb is now lit. The bottom bulb or device or whatever's there is no longer energized. So in example 2, switch 1 has been closed. This has energized the relay coil C1. When the coil was energized, the normally closed contact becomes open and de-energized the second bulb. The normally open contact becomes closed and energized the first bulb. The Mars brand relay is one of the most frequent relays you'll see in the field. It consists of a coil and 2 sets of isolated contact. Each has a common, a normally open, and a normally closed. This is a picture of the face of the relay. Now you can always refer to the diagram that's actually imprinted on the plastic here. This is pin 1, pin 2, pin 3. 1 to 3 is normally open. 1 to 2 is normally closed. It is repeated sometimes with 4, 5, and 6. However, there is no electrical connection between the top with 1, 2, and 3 and 4, 5, and 6. You can actually control 2 different circuits and 2 different voltages on this. The pins down here at the bottom are the coil connections, and they give you 2 pins, but they're connected to each other. So you'll put whatever's there. You'll put like if we're dealing with low voltage, you'll put your red here and your common there, or L1, L2, or L and neutral. So your coil is a load. This is just another relay. The picture's a little bit stretched out, but same principle applies. You have your coil down here, and you have your switching up here. It's a normally open, normally closed. Just a slightly different look. So the internal schematic of the Mars relay, again, shows exactly how it did on that other, printed on the face. We have 1, 2, and 3, 4, 5, and 6, and our coil. Each section, by section, is not connected. So 1, 2, and 3 is independent of 4, 5, and 6, independent electrically of the coil. Now mechanically, when the coil gets energized, they affect both of these groups at the same time. Troubleshooting relay is a matter of looking at the voltage across loads and switches. In the following example, B2 is not working when switch 1 is turned on. Okay, so we have a relay here. B2 is not working, okay, even though switch 1 is turned on. So first, make sure the circuit has power across L1 and neutral. Okay, we have 120 volts. Next, close switch 1 and check from L to line of switch 1. We have 0 volts. Tells me that there's no break in that circuit. It's good. Now check from L to the load side of switch 1. 0 volts. Switch 1 is closed and is working properly. Line to line side of C1. 0 volts. Tells me my wiring is good. Line to neutral of C1. We have 120 volts. That tells me my coil is getting power. Okay, remember, voltage across a load is always going to be source, unless it's wired in series with something else. Here it isn't. L to neutral at the end of the branch, still have 120, we're fine. Tells me why my wiring is good across the control branch. Now, we're going to check L to the line side of C1 contact. We are fine. L to control side, 0 volts. Tells me it's a good circuit. L to line side of C2, 0. Tells me the contact C1 is actually closed. L to neutral of C2, 120 volts, tells me C2 is getting power. And again, we're going to check just to make sure we don't have something odd going on. We'll check from L to neutral of C2 coil at the end of the branch. Okay, so far we've established that C1 is getting power, is properly closing this C1 contact, and is energizing the C2 coil. Line to C, line L to line of C2 contact, 0 volts. Tells me there's no open. 0 is a good number when we're looking for continuity. L to load of C2 contact, we have 0 volts. We are fine. L to line of B2, okay, we are fine. We have 0 volts. Tells me this contact is actually closed. Now, L to load of C2 contact. Okay, now we're checking across a load that's supposed to be energized. I have 0 volts here. This is a bad reading because remember, voltage across a load that's energized should be source. So we know we don't have a proper voltage here. I had good voltage here, but I don't here. L to neutral of C2 contact. Okay, I have 120 volts. Okay, now here's where we start having a problem. Okay, right here. Tells if I have voltage across any switching device, it tells me that that switching device is open. So based on the last two measurements, the technician would determine that the contact or relay C2 has a bad contact. Voltage across a load should not be 0. Voltage across a closed switch or contact should not be source. So here we got source, and here we got 0. Tells me right there that that C2 contact is a problem. Now, on the schematic, I did leave it open, okay? But in real life, in the field, this would be in a box, and you wouldn't be able to see if this is open or closed. So that is what I can give you about relays, okay? Again, normally open, normally closed. The coil has to be energized with the appropriate voltage. Contacts have to be rated properly for the load. And troubleshooting is done with a voltmeter most often in a circuit to see if it's energized, de-energized, open, or closed.